So coming back to, like, as the name suggests, I'm going to talk about knots. And knots, even if you don't do maths, from the childhood, you know that you deal with knots. When you tie your shoelaces, you have to make knots. And then you also know that if you don't tie it properly, it opens up. And then you get scolding from your parents that, oh, you fell because you didn't tie it well. And in several places, you will see that, like how to knot or whether the knot is truly knotted, all those questions. How does mathematics come into the picture? That's the question. Like, why are we doing knot theory in mathematics? So, if I just take a piece of wire and I just try making a knot out of it, suppose I just do this, what am I doing mathematically? So, this is my first slide. You take a piece of wire and you just try making this. And now, if someone tells you, describe it mathematically. So, what does that suggest? If you have to, because now you all are exposed to describing things in terms of functions, right? So, this is a one dimensional object, it's just a wire. And if I think about the ends being loose, suppose I don't really fix the endpoints, then it's like an interval, right? Open interval. And if you are familiar, you know open intervals are homeomorphic to real line, whole R. So one could think about this as like, forget about the ends or think about ends going to infinity. So it's like R. And the knotting that you're doing, you are sitting in a three-dimensional space. So basically, this whole process of doing it as if like your graph is going by some functions. So those three coordinates, like R going in R3, you require to describe X, Y, Z three coordinates, and they should be the term called embedding. So what it means to say embedding is roughly is like the map should be 1 1, like it shouldn't cross. So in three space it's possible, like you can go over and you're not really crossing, and you can go under, you're not really touching, and you are actually, the map is 1 1, even though here it looks like touching, but in three space you can make little up and down. So the map is 1 1, but only 1 1 as a map is not really sufficient for embedding. So the another thing is the derivative map. That also you are familiar with, right? Given any function, you have its, if the function is differentiable, you can write down the derivative map. So if the map is 1 1 and the derivative map is also 1 1, then such a map is embedding. So the process of tying a knot can be described as if you are writing down an embedding from R in R3. Now the next question comes, we make several such knots. Now, suppose you want to see, sometimes I can make something fake, in the sense like I do this, I say it goes up, then again it goes up, and it's looking like going up and down, but if I pull, it's not. It's really an unknot. It's not really got it knotted. So you can always try to simplify to see whether it is actually knotted. So what it is simplifying means mathematically, I will explain that. Now, while simplifying, if you have open ends, sometimes it might happen that the knotting is towards the end. And when you pulled, the knotting was towards the end, but because you pulled carelessly, it got unknotted and you thought it was not knotted. So there is a chance of mistake happening. So how does one avoid such a mistake? So to avoid such a mistake, mathematicians deliberately tried that we won't take open end. Whatever the map is, let's try to glue the ends. So if the knotting was there, you close the ends and then you try simplifying. So then the mistakes won't happen. So if the knot was there, it will remain knot. And if it wasn't knotted, it will still be simplified. So then what are we doing? Now initially it was open-ended. So it represented real line, R. But when the ends are united, in, in topology, which you may learn later, there is something called compactification. So what we are doing is we are trying to add those plus infinity and minus infinity together, and we are obtaining a new space. And what is this new space? Can you identify? Circle. So circle is also one dimensional, but it has different properties. It's compact. So now the ends are, and we could now think about embedding S1 in 3 space. Now 3 space, we can think about not as embedding of S1. S1 is a notation used for circle, like R is used for real line. So S1 is for circle, and that's the definition. But to make it look more symmetric, now the three-dimensional space sits inside three-dimensional sphere. If you have heard of every dimension, there is a sphere of that dimension that you compactify this. So S3 still you can imagine, but if you have to imagine S4, S5, it's hard to imagine. But in principle, we can describe. We can just describe n plus 1 coordinates such that the sum of the square is 1. So you have Sn, and here knots are embedding of S1 in S3. So it's a classical knot definition. Then it comes to, so this is what definition mathematicians will take, and you could describe it because these circles, when they go inside 3 space, you can avoid using the term embedding, and you can say that it's a simple closed curve. That anyway in first year, semester 2, if you have, I don't know, in IISER Pune, it's in semester 2, whatever the calculus 2 course, you do learn simple closed curves. So simple closed curves inside S3, that is your definition. And by equivalence, so here I have just described this wild versus tame knots. So if I wasn't insisting on the differentiability part, so I use the term embedding, but we are taking smooth embedding, like the map is actually differentiable as many times as you can, smooth embedding. So there are those bad things don't happen. So there is a, like if you know, you must have gotten examples that there are functions which are infinitely continuous everywhere and nowhere differentiable. So they might, like you can go on writing, making loops infinite number of times, and they can create bad examples. So the knot theory subject is focused only where there are finitely many times they cross, and that's what is tame knots. In other words, you can also describe them using piecewise linear functions. Like if you could draw a knot using only, like there are rods and you are just placing them in three-dimensional space, putting them under and over, and if you could write, that is what is your tame knot. Now that little bit of a history. So why did this knot theory become so important? So initially it was, see, if I say embedding of circle in S3, so all knots are topologically, they are all S1. As an object, they are all circles. It's just that how is circle sitting inside? So what it is not that important. How it is sitting is more important. So that is what was considered as geometry of position, and it was discovered in 1771. The most popular thing came when there was a theory of atom. The physicists, this Lord Kelvin, they were trying to study how like what periodic table is right now. So in that era, when they were trying to make a periodic table, it was proposed that every atom is made of some knotted tube of ether. So they thought that if they could classify all knots, then that would lead to a table. And in their collaboration, there was a mathematician whose name was P.G. Tate, and he took this as a project. He was a discrete mathematician doing combinatorics and all. He was good at those things. So he took that as a project that he would enumerate, try to find patterns and classify all the knots. And later on, the physicists lost interest because they thought that they found that theory wasn't true, and then they shut their interest. But mathematician Tate, he still continued because it was fun for him to classify all knots, and he made a table, and the table was actually based on a lot of conjectures. He prepared certain rules and followed them, and those rules and conjectures that he formulated, many of them he couldn't prove, but he believed them and he made the table. And those conjectures got proved very recently when recent knot theory research took more progress. So now we could generalize knots to links. So like if you have one circle embedded, suppose you have a bunch of circles, there are 5 circles, and you are embedding them in 3 space. So when you define the map, every individual circle can get knotted, and also in that process, maybe one circle and other circle also can get linked. So you can have links with many components, and one can just take links and think about knots as linked with one component. Like if it's connected, then it's a knot. So one could study links, and then one could try defining what we mean by 2 knots or links being equivalent. In mathematics, everywhere when you define a structure, there is an equivalence. Like when you study sets, equivalence is like when you would consider 2 sets to be same if there is a bijection. When you go to other little more advanced, you put a structure, group or something, then the equivalence slightly gets more rigid. So similarly, 2 knots or 2 links, we would like to know exactly when they may look different, but how do I know they are same? So in layman's language, I said, take the knot, don't cut it, don't destroy it, just play with it. If you can simplify and transform one to make it look like the other, then you would say they are same. But that's not a mathematical definition, because you can't really describe this. How are you simplifying? So here, see these pictures that I drew. The first thing, it looks like you can, because you just need to untwist it, right? You just have certain things like loops, and this loop, I can always pull it like this, and it would become the same. But the second diagram that I made, so if you pay attention, A and B, they look similar because they both have crossed 3 times, but the where something is under, that becomes over here. So mathematically, this one is actually mirror image of the other. If you put a mirror, then this one will be on the other side in the mirror image. So these two are mirror image of each other. And now suppose I make this knot and I try simplifying, I cannot convert it to make it look like this. But how do I know that what I'm unable to do is actually true? I can't say just because I can't do it, these two are not equivalent. So we need a solid definition. So the definition says, so both of them are embedding of S1 in S3. So let me use the chalk. So suppose you have S1 to S3, there are two maps, phi1 and phi2. They lead to their images are two knots, say K1 and K2. And I want to say they are equivalent. So roughly what we are doing, the process of simplifying, I am trying to describe some kind of motion is happening in the S3 level. So from S3 to S3, if I can get a good map, which is described as orientation preserving diffeomorphism. If you don't know these terms, the definition of this, just believe that with some good property, and this represents how S3 shakes such that if you compose one of them with this, you should get the other one. So saying that this transformation, I can convert one to the other, can be described mathematically like that. And this orientation preserving is very important because if I don't put orientation preserving, then every knot will be equivalent to its mirror image, which is not the case. So this orientation preserving plays an important role because we know all knots, there are knots which are equivalent to their mirror images, but there are knots which are not. And in chemistry, such a property, if you treat knots like molecules, then it's called like it has chiral property. That is also well known. That's how knot theory is used in chemistry because they are very much interested in learning about chirality. So that's how you define equivalence. But now the question is, I give you two knots and you have to show or check whether they are equivalent. It's hard to check they are equivalent. It's easier to check they are not equivalent, at least eliminate. So how do I do that? It is very difficult to use this definition that defining such an H such that if I compose the first, I will get the other. So from the definition, it is certainly very hard. So what knot theorists do, they define, they associate some quantities or properties or structures, lot of things. Given a knot K, they try to associate something, let's call I of K. That I of K can be a number or a group or a set or polynomial. And that is what we call invariant, not invariant. So not invariants are something which are preserved under equivalence. So if we compute, given two knots, if I compute its that particular invariant, and if I detect that they are not same, then I can say they are not equivalent. It would be very ambitious to find such an invariant such that it's if and only if. But most invariants are only one directional. You only have things like if K1 is equivalent to K2, then IK1 is same as IK2. So its contrapositive will be if it's not, then they are not. But we don't have this sort of results. So we don't really have a good complete invariant, but still at least something, at least we are able to. So knot theorist, the whole research is to find good invariant, because give some invariants are able to detect two knots being not equivalent, but then they can't detect other pair. So now these are the relevant questions. So whether, first of all, if you have an invariant which can detect knot from unknot, that also is like there are invariants which are not able to. And then, because we are interested in chirality, can the invariant differentiate a knot from its mirror image? So till date, there isn't like any invariant which can completely answer. There are theoretically some invariants, but then they are not that easy to compute. Even if you abstractly define something, but if you want to really use it, given a knot, you should be able to compute that. Then only you can say that I found it. So there is no use if it only exists in theory. So some initial invariants. So now here, this was something I don't know if you're familiar with. So given a knot, there is a group attached to that, which is called knot group. And that group in topology is basically you take the complement of the knot, and there is something in topology called fundamental group of a topological space. And the result is, if the knots are equivalent, then their groups are isomorphic. So if you can prove that the groups are not isomorphic, then you at least know that the knots can't be equivalent. But this invariant is good for knots. It can detect like only for unknot. It has the specific group, which is the group of integers with plus operation. That's for the unknot. And it is if and only if. Only for unknot it is. So if the group doesn't turn out to be Z, then the knot is not unknot. But then this invariant is not good for detecting chirality. So any knot and its mirror image, the group is always isomorphic. So the invariant is not that great. So anyway, so now how do knot theorists define invariants? So how do they do to find more and more invariants? Because we need to have a complete some working thing which can help generating invariants. So the first approach is by representing knot by a diagram. So if you think of it, we are dealing with knots which are in three-dimensional space. Now, hanging it in three space, we can't really work with it. So when we draw it in a plane. So roughly what we are doing is we are first projecting it into a plane. So from R3, we come down to a plane. Now the question is which plane? In three-dimensional, there are a lot of directions. And any direction, you can have a plane perpendicular to it. So if you randomly project, the information might be lost. Because if I have a lot of crossing in this direction, crossings, and I choose a plane perpendicular, it will all collapse to the same point. So the question is, how do I choose a plane? So that again, because we are in tame knot, it's been proved by algebraic geometry that that kind of argument that we can always find such a plane where if you project, the projection should not have triple points. Projection should not look like B or C. That strand shouldn't go tangential or a cusp. So the projection should look like how that picture is. But once you projected it, the information about under and over is lost, because in two-dimensional they will cross, they will touch. So they become double point. So that's a projection, and such a projection we call regular projection. There can be many regular projections, it's not unique. But once you projected it, at every double point, you can give information about which one is an over and which one is an under strand. And that we can represent by making a cut. So when we draw it like this, we call it a diagram. Now, given a knot, so any knot we can represent by a knot diagram. Now, knot diagrams are many. For a given same embedding, you can have several diagrams, because you could choose another plane and get another projection. So now, how do I know at the diagram level, two diagrams are representing the same knot or different knots? So for that, there are, at diagram level, there are moves, which are like you could very easily believe that this is what should be the case. The first move is just a twist, just untwist them. The second one is you have a strand and another strand is going under and under. All you're doing is to pull them apart, which you know you can do it and it won't make a difference. And the third one is if you have a three strands, so the under one is, see, the under one is under, under, under. So you could just slide it up. So it's called slide move. So these three moves, they completely describe they capture the equivalence at the diagram level. So you say the diagrams represent isotopic knots. The equivalence in knot level or link level is called isotopy. It's an if and only statement, which so that one diagram can be described by a sequence of finitely many diagonal move. You may not be able to transform one diagram to other by just one move. You may require several moves to be able to, and sometimes it is not visible. You can see a diagram and you may not see that you can actually transform. See, this particular knot, the leftmost, it has 4 crossings. It's a very popular knot. It's called figure 8 knot. And this is equivalent to its mirror image. But if I see this and this side by side, it doesn't give a good impression that how do I use Rider-Mister's move. So sometimes, see, you see that Rider-Mister move is artificially used to create more crossings and then simplify, and then, so there are so many, like 1, 2, 3, 4, 5, 6, 7, 8. The 9th step, we are able to transform this to its mirror image. So it's a theorem, but then how many Rider-Misters move you need, all that is like, again, a question, like how do you transform one diagram to the, it's not that easy. So now the invariants, if I am defining an invariant using diagram, I need to check that that quantity does not change under these 3 moves. So I take a diagram, I define something, and then I have to verify if I perform Rider-Mister move 1, the quantity should remain the same. Likewise, Rider-Mister move 2, 3, the quantity, if it doesn't change, that means that quantity is a link invariant. And we can use them for detecting. Another approach to discuss, like represent knots, which has been used, is using braids. So braids are again objects which I'm trying to like very quickly go through because I have very little time left. So yeah, braids are like you make a plait, you know, there are strands. Suppose I have 3 strings and I am just trying to put one under the above and like this. So you just make the paths, and given this is how, suppose there's a 3 strands, we would call them if 1 and 2 cross and 3 remains, we call it sigma 1. And if it just flip it, it's inverse. So likewise, we can have, if you had n strings, you would have n minus 1 such sigmas, and they form a group. And okay, so all these groups are, I'm skipping this. So the idea is, if you have a braid, suppose you take a braid. So you have 1, 2, 3, 1, 2, 3. You just try joining 1 to 1, 2 to 2, and 3 to 3. So if you had n, join each one to itself, then you see that you will end up getting simple closed curves. And sometimes you might get a knot. It depends upon the permutation. If it's a cyclic permutation, like here, my 1 is going to 3, 2 is going to 2, so it's not cyclic. 3 is going to 1. So you will get how many cycles? Those many components. So the observation is, if you perform such an operation, you will get a link. Sometimes you may get not. But the good thing is, the Alexander proved this theorem. Yeah, every link is isotopic to closure of some braid. And that helped in putting a bijection that every link, you can get some braid whose closure is it up to equivalence, and closure is a link. And then at the braid level, also we have some equivalence which takes care of, if there are two braids giving the same link, then they are also related. And braids can be used, this representation also can be used for defining invariants. Now, one interesting invariant is this colorability from the diagram. So suppose you have a diagram and you are supposed to use at least two colors in the diagram, and at every crossing you should have either same color is used or three colors are used. So here you see that we are using three colors, and at every crossing, three colors are used. So such a diagram we'll call a tricolorable diagram. And this turns out to be a tricolorability is an invariant. It's been verified that it's invariant under all three Riemann-Strauss move, and that can be used to prove that the trefoil, the three crossing knot and unknot are not equivalent. Here, the trefoil and the figure eight are not equivalent. One could just use the tricolorability, and see, this diagram is not tricolorable because here we are trying to use four colors to be able to, at even though it is satisfying at every crossing there are three colors used, but then the number of colors in general is like more than three. So, but using tricolorability, it's not easy to, like, there can be very complicated diagrams. So that coloring is generalized to n colorability, and those kind of things are there. And for the group also, from the diagram, there are like ways to compute the group that I talked about. So I'm skipping right now. But then the next thing which is important is giving some kind of orientation. So the diagram I made, now if I put an arrow, we can call it an oriented diagram. And once orientation is there, then at every crossing, we can give some kind of notion for positive and negative crossing. So if the over one moves anti-clockwise, we'll call it positive. And if it moves clockwise to join the under one, we'll call it negative. So when you have signs, you can add it up and you get a number which is called right, but that's not invariant. Now, what I'm trying to say is this question of any invariant being computable. So let's focus on that. There are plenty of invariants in this such 50 minutes. It's difficult to discuss them. But the question is, given an invariant, can I compute? Is there a mechanism that invariant can be computed? So there are some invariants of a very special kind, and they are based on something like induction. So the principle of induction is what? You know that there is a base step. If it has to be true for one, otherwise there is no point in moving. Then you say that if it's true, you assuming it's true for k, it must be true for k plus 1. Then that's what you are saying. Since it's true for 1, it has to be true for 2, it has to be true for 3, and so on. And that's why it's true for all. So likewise, some invariants have this thing that for the base step, suppose I know the value for the unknot, and I know the invariant, somehow it values for lesser complex knots, then can I combine these two to be able to compute it for the next knot? So that is the idea. And the complexity of a knot, now how do I measure the complexity? So first thing is, if you had seen, since my knot and link is crossing only finitely many times, so suppose something crosses only n minus 1 times and another one crosses n times. So I will think that less it crosses, it's less complex. So that's one thing. So given any knot, so for instance, suppose I am drawing this 3 crossing knot. Now, if I see here, this is an under and over and under, and I'm putting, suppose, an orientation. At some place, if I switch over to under, switching a crossing, the assumption, like you can verify that switching a crossing reduces the complexity. In this case, the moment I switch anywhere, it becomes a knot. Because see, you can use Reidemeister move 2 to both of them are over. So it will become like this. And then Reidemeister move 1 and it will become 1. Right? So switching a crossing is an operation which reduces the complexity. Another operation is, suppose this is my orientation. I am putting that. So at any crossing, I bypass. Instead of crossing, my following the orientation, I just bypass the crossing. And this process is called smoothing. So the moment I did the smoothing, the number of crossing became less. And that's why my complexity has reduced. So these two operations reduce the complexity. I'm skipping this also. So now suppose I have 3 diagrams. I'm trying to develop like how we can compute an invariant. And my 3 diagrams are identical everywhere except at one crossing. And at one crossing, one of them has a positive, another one has a negative. That means I switched. If I switched from over to under, positive will become negative. And the middle one is the smoothing. So 3 diagrams are like that. And the invariant has this property that it satisfies this linear relation. So suppose my invariant is taking values somewhere in some, see I'm saying in a ring R, and we have 3 invariants, A plus, A minus, A naught, which are invertible in the sense like their inverse exists, and they satisfy this. Along with their value for the unknot is say constant 1. Constant 1 is just a convention. I can put constant C. All I want to say is it should be known for the unknot, and it should be satisfying this sort of relation. Then such an invariant can be calculated, and that will depend uniquely on these three coefficients. And there are class of invariants which have this sort of property. It's just that these coefficients may keep changing. One invariant for that, a plus a minus a naught, will have some choice. That's an invariant. There's another set, another invariant, but they are computable and they are called linear skein invariant. All invariants are not skein invariant. So some very special, so someone proved that such an invariant exists using braid theory. Now, these are interesting polynomial invariants. We call them polynomials, but they are actually, they have negative powers. They are Lorentz polynomial, and they even have fractional powers, t to the power half and so on. So if, see, it is defined in a very abstract manner, but this property that it is keen, it helps in calculating. So this Alexander polynomial, its value for unknot is 1, and it has, so its a plus is 1, a minus is minus 1, and a naught is this t to the power half minus. So using these two relations, we could just compute Alexander polynomial for any knot. It will take a lot of time, because crossing by crossing you would perform those and go to the smaller one, then compute that. So, but still you can compute. But Alexander polynomial has a drawback, that it doesn't differentiate a knot from its mirror image. And it also doesn't detect a knot. There are non-trivial knots with polynomial 1. So it wasn't like, even though it is very well understood, but it's not that useful. Then we have Jones polynomial. This was something I really wanted to tell. So this was discovered in 1984, and this brought the major breakthrough. This was the first invariant which was successful in differentiating a knot from its mirror image. And also all the Tate's conjectures, which were not proved for 100 years, they were all proved using Jones polynomial. And this person, Vaughan Jones, who discovered it, he got the highest award called Fields Medal for Mathematics, and that was given to him in that year. So this was a very powerful invariant. And then the same invariant, because of skein theory, because if two invariants satisfy the same skein relation, they are same, it was reinvented using diagram theory completely by Lou Kaufman. Jones defined his Jones polynomial using braid, very advanced operator algebra approach, but he proved that these skein relations are satisfied. And Kaufman used diagram theory to define some invariant. Later on, they proved that those two invariants are actually the same. So this became another definition for Jones polynomial. So I'm again skipping. I had just 5 minutes, so wait. So I can help you compute some of the things. But anyway, Jones polynomial also is not 100% perfect. So it still is open. So Jones polynomial for unknot is 1, but no one is able to prove that given a knot, if Jones polynomial is 1, then that knot has to be a knot. So that's not still, that's an open question. And no one has even found a counter example that, look, this knot I know is not an unknot, but still Jones polynomial is 1. Like Alexander polynomial is settled, because we found examples where Alexander polynomial is 1 for a non-trivial knot. But for Jones polynomial, it's still not known. But for the pair, there are knots which are different, but their Jones polynomial is same. So Jones polynomial also is not like a complete invariant as such. So one wants to define more advanced invariants which could detect. So there are a lot of advanced algebraic topology machinery, like if you learn some homology theories. So there is some homology theory called Khobanov homology that turns out to detect unknot. Like there are theorems which say if a knot is an unknot, if and only if its Khobanov homology has to be this. So the Jones polynomial, which was defined using braid groups and so on, since still is not a refined invariant, best invariant, so how do we generalize and find more strong invariant? That came as a question. So again, after Kaufman also, there was a third approach to try that look at Jones polynomial coming from some quantum groups. Now, quantum groups is another branch of mathematics that you can learn if you're interested. Using that, Jones polynomial could be produced by some kind of representation theory. And that opened a door for generalizing, because there is a special quantum group which is denoted by SL2C. Now, 2 is just because there are 2 by 2 matrices. Trace 0. So set of all 2 by 2 trace 0 matrices are SL2C. Their quantized version, it's representation theory, and a very specific representation, two-dimensional. So SL2C and two dimension. So there are two ways to generalize. You keep SL2C as SL2C. Instead of two dimension, you say I'll take three dimension, four, n dimension. That gives a sequence of another invariants. Then you fix a dimension and change SL2C to SLNC. That gives another set of invariants. They call it colored Jones polynomial. And those invariants are more refined than Jones polynomial. So, okay. Now, I will conclude by saying that this knot theory, even though it's like you must have got this impression that the tools are very much like abstract, very lot of strong pure mathematical techniques are there to define. But the applications, the knot theory has been applied to other sciences, even in other areas. So in biological sciences, for instance, like designing a lot of medications, the drugs. So there, this DNA analysis, the whole thing is about this switching, this crossing. I told you that if you switch over to under, the knot can become unknotted. Maybe you may switch 3, 4 more number. Here, in case of this knot, only one switch was enough to unknot it. But in some other more complex knots, you may require more changes. But if you make several changes, that's also the least number of changes needed is an invariant. That's called unknotting number. So a knot can become unknot. But how does this being useful there is in our own body, we have a natural enzyme called topoisomerase that has the property that it actually makes a cut and flips under to over. So if one could produce a medication, some drug which stimulates that enzyme, then if there is a knot formed, that knot can get unknotted. So this has been used, and knot theory has been used in protein folding, understanding protein structure. And more importantly, these days, you must have heard that in many years to come, there will be only quantum computers. So quantum computing and knot theory, the knots are the very good objects for building quantum computing, even though I don't understand at present, but I just have this thing that it can be useful in quantum computing. So I will finish my thing here and open to questions.
Thank the speaker once again.